Good evening. This is problem solving session for course Basic Electronics offered by NPTEL with the code NOC23EE62. This is week 10 on April 8th of 2023. My name is Amit. I am a PhD scholar at ISC Bangalore, and for the past 9 weeks we have been solving problems of some previous year assignments for this basic electronics course. And till this time we had talked about from starting from session 1, Thevenin and Norton equivalence, nodal analysis and superposition theorem, how to use to solve the basic circuits, and then phasors, which we saw, which were nothing but sinusoidal steady states for currents and voltages. Then the second session, we added some complexity by talking about the transients, primarily RC and RL transients. And then we also talked that how does switching impact the transients. Finally, we switched into some semiconductor devices, primarily diode-based circuits, which involved clamper circuit and peak detector circuits. And then we continued with diodes to study the half-wave rectifier. And then we jumped to BJTs, bipolar junction transistors, and how does the DC biasing impact the currents and other things in a BJT circuit. Then we went on a very common application for BJT, that is common emitter amplifier. And then within that we talked about the small signal equivalence, that is hybrid pi model and T models, is the two models that we had talked about. And basically in this we talked about the AC or the small signal analysis of a BJT. In biasing we talked about in the DC biasing, the DC you say current and voltage. In small signal analysis we mainly talk about the voltage gain, because you want it to use as an amplifier. And then one of the applications we saw was in the form of push-pull amplifier. Finally, we moved on to op-amps, and in the session 6 we talked about ideal op-amp circuits, in which we saw virtual ground and what do we mean by negative and positive feedback. Session 7 we talked about some non-idealities in operational amplifiers, that is the offset current, offset voltage, and so on. And then one application which was difference amplifier. We saw quite a few examples based on this. In session 8 we added some more complexity, and we talked about precision amplifier, in which if you go back you can see there are some diodes involved, and how we can use different devices to suit our needs. And then finally we saw op-amp as filter. This is one of the most commonly used applications of an operational amplifier. We used how to use it as a filter. And then therein we talked about the transfer functions and Bode plots, and what is the slope of a pole. The Bode plots are two, that's magnitude Bode plot and phase Bode plot. We had talked about that. And finally in the last session we had talked about positive feedback in operational amplifier, in which are essentially oscillator circuits, and one of the most common examples is the Schmidt trigger. And we saw that how can we create square waveforms, and then using some different topologies we can also create a triangular waveform, which we saw in oscillator circuits. So for today's class and for the next two classes, that is for last 3 sessions that we have, we'll be talking about digital electronics. Okay, so let's get started with that. And this is the first question that I have, that you must have on your screens. Excuse me, just a second. Yeah, so we are good. Okay, so this problem says, just consider a logical function x equal to p plus q plus r bar. This is in a bracket dot. We'll just see in a bit what this means. P bar plus q. Which of the following truth tables correctly describes this function? So we are given this function x, and we are required to find what is a truth table. So what do we mean by truth table? Let's just quickly get into that. So truth table, to put it very bluntly, truth table is nothing but I should say it like this, is a list of all possible combinations of inputs and corresponding outputs. So what we'll do essentially is that we'll list whatever the inputs that are possible in that system, and then given the system, we'll try to evaluate the output. It's very simple. So let's just take one of the most simplest systems, which is a NOT gate, also known as negation. Okay, this is the symbol, by the way, a triangle followed by a circle. So in this I have one input coming A, and I have this output as X. So what I'll do while populating the truth table, first I'll write in the first row, I'll write all the possible inputs and outputs. So in this only one input x, a, and then we draw a vertical line just to demarcate the boundary between inputs and outputs, and then I write x. Okay, so there's only one input. The input can be either high or low. So that's why you see 0 or 1. Okay, now I'll go to each row. I'll go to this row first. The first row I'll say when the input is 0, and I know this is a negation, so whatever is coming, the output should be invert of that. So x would be 0 bar. X would nothing would be 0 bar, which is nothing but 1. Similarly, in the second case, when the input is 1 and the input is high, excuse me. In the second case, when the input is high, the output should be again negation of the input. So it will be 1 bar. 1 bar is nothing in Boolean algebra. 1 bar is nothing but 0. Zeros and ones usually denote low and high. So if we see in analog world, so this is analog world, let's say 0 volts and 5 volts. In digital world, this we denote it as 0 and this we denote it as 1. So there are only two stages. There is fuzzy logic in which there are more than two stages, but for our complete discussion, we'll just stick there are only two stages possible, 0 and 1. So it can either be high or low. So the negation of high will be low. So 1 bar, thus it's 0. So this complete thing which you see over here is called a truth table because it lists all the possible, that's what I say, list of all possible combinations of inputs. So what are the possible combinations? A can be 0 or A can be 1 and corresponding output. So I obtained the output corresponding to each row. Okay, let's do one more example. In this case, we have an AND gate. AND gate is denoted by, this is a 2-input AND gate. This is the symbol. The two inputs are A and B and the output is X. What I'll do if I want to make the truth table, I'll write combinations of all the inputs. So there are two inputs. They can be 2 raised to the power 2 possible combinations. That is, A and B both are 0. B is 0, A is 1. B is 1, A is 0 and both are 1. Then what I'll do, I'll one by one, I'll evaluate the output. So output is nothing but A into B. If there's nothing in between, we denote it by a dot. A times B. Low times, so here low times low. So 0 times 0 will be nothing but 0. 0 times 1. 0 times 1. Note this formula. This will be nothing but 0. 1 times 0. 1 times 0 will be nothing but 0 again. And 1 times 1 will be 1. These are some rules of Boolean algebra when we talk about digital electronics. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0 and 1 times 1 is 1, and hence you get this output. So this is the truth table for an AND gate. I deliberately took very simple examples so that just to put this point very clear, that truth table is nothing but a list of all possible combinations of inputs, and then based on the expression that we have for output, we evaluate the output. Okay. Now coming back to our problem, now once we have established that what we are talking about in this case, we'll come back to our problem. So this was the problem that was given to us. We want to obtain the truth table for this expression. Now first thing that we note is that what are the inputs and what are the outputs. So this is the output clearly because it's on the left hand side. So X is the output and X is dependent on three inputs which are P, Q and R. You can also say it's also dependent on P bar and R bar, but what I'll take is non-inverted is what I'm taking as the input. So I'll take the input as P, Q and R. If I know R, I can obtain R bar. All right. So that's what I do here. So the inputs that I have are P, Q and R, and the output is over here. Okay. But in order to go from input to output, I have to evaluate first this quantity, P, Q plus R bar, which I'm evaluating over here, and the other quantity P bar plus Q, which I'll evaluate over here, and finally I'll multiply them to get the value of X. Okay, and as I told you, list of all possible combinations of inputs. So there are three inputs. So how many rows are possible? 2 raised to the power 3. So 8 rows. And what are those values? You can see that the first is 0, 0, 0 when all the three inputs are 0. So let's try to populate this row first. Okay, when P, Q and R all of three are 0, P bar will be nothing but 1, 0 bar. This will be nothing but 1. R is 0, so R bar will also be 1. And let's evaluate P plus Q plus R bar. The value of P is 0, value of Q is also 0, value of R bar is 1. 0 plus 0 will be 0, 0 plus 1 will be 1, this will be 1. P bar plus Q, P bar is 1, we have evaluated, Q is 0, so 1 plus 0, this will be 1. X is nothing but the multiplication of these two terms. So that is 1 times 1. So the value of X that I have obtained is 1. So I have now completely evaluated this row. That's what I mean. You first list all the possible combination of inputs, and row by row we go on evaluating the output. Now let's quickly do the second one. So P bar, P is 0. So this will be 0 bar, which will be equal to 1. R in this case is 1. So 1 bar will be 0. And then P plus Q plus R bar. So the value of P is 0, Q is 0, R bar is also 0. So this will turn out to be 0. P bar plus Q, P bar will be 1 and Q is 0. So 0 plus 1 is nothing but 1. 0 times 1. 0 times 1 we have seen in the last slide. This is nothing but 0. Let's do it again. So 0 bar, this will again be 1. R is 0. So 0 bar, this is 1. P plus Q plus R bar. The value of P is 0. Q is 1. R bar is 1. So this will turn out to be 1. P bar plus Q. P bar is 1. Q is also 1. 1 plus 1 is 1. High, and if you add something high value to a high value, it will only be higher. That's why 1 plus 1 is equal to 1 in this 1-bit Boolean algebra. Then we get 1 times 1. This is equal to 1. Let's do the fourth row. 0 bar is 1. R bar, 1 bar is nothing but 0. P plus Q plus R bar, this is 0 plus 1. I'm going through them very quickly because it's just repetition. R bar is nothing but 0. This will turn out to be 1. P bar plus Q. P bar is 1. Q is 1. 1 plus 1 is 1. Again 1 times 1. This will turn out to be 1. Alright. Now let's evaluate P bar again. So this is the value of P is 1. So 1 bar, this will come out to be 0. R is 0. 0 bar will turn out to be 1. P plus Q plus R bar, this is 1 plus 0 plus R bar is 1. So this will turn out to be 1. P bar is 0. Q is 0. This will turn out to be 0. 1 times 0 is nothing but 0. Again 1 bar equal to 0. R is 1. You can see it here. 1 bar is 0. P is 1 plus Q is 0 and R bar is 0. This will turn out to be 1. P bar plus Q. P bar is nothing but 0. Q is 0. This will turn out to be 0 again. So 1 times 0 is 0. Alright. This will 1 bar again will be 0. 0 bar is 1. P plus Q plus R bar. P is 1. Q is 1. R bar is 1. 1 plus 1 plus 1 is nothing but 1. High, high and high. P bar plus Q. P bar is 0. Q is 1. This will turn out to be 1. 1 times 1. This is 1. P bar is again 1 bar equal to 0. R is 1 bar equal to 0. P is 1. Q is 1. R bar is 0. This will turn out to be 1. P bar plus Q. P bar is 0. Q is 1. 0 plus 1 is 1. 1 times 1. This will turn out to be 1. Now what I have done is that I have evaluated the output for all the possible combination of input. This is nothing but the truth table. But what we do is that we do not report these intermediates. Okay, we are just interested in the output here. Okay, so what I'll do, I'll just skip these four columns in the middle, and what I'll do is I'll just write the inputs and the final output. Okay, just remember 1011 0011. So it's 1011 0011. I'll write here 1011 0011. This is the output that we have obtained. So let's see, 1011 0011. Okay, so option A matches. Let's check other. This doesn't match because 1011 this also doesn't match. 1011 this also doesn't match. So we can clearly see that option A for the first problem matches the values of X matches that we had obtained in this slide over here. Just to summarize, a truth table is nothing but the possible list of all possible combinations of inputs which you see on the first three columns, and then the corresponding output, and we had evaluated using some very basic Boolean algebra that we see over here. All right, so any comments, any questions till this point? Because truth table is actually the one of the most fundamentals of digital electronics. So if not, then okay, then let's move forward to second problem, which you can see on your screens. So the question asks, which one of the following functions is equivalent to the Boolean function this? So we have been given a Boolean function which is over here, a equal to something like this, and these are the four options. So what we are required to do, we are required to simplify this expression to reduce it to the simplest form essentially. All right, so we'll do that, but first let's just quickly have a brief overlook of the Boolean algebra. So the Boolean algebra, there are three primary operations. Okay, first is what you call the conjunction. Conjunction is nothing but your AND gate or your multiplication, that dot which we saw. Okay, disjunction is nothing but your OR gate, or also denoted by a plus sign. Negation is nothing but your NOT gate, which we saw in the second slide. So NOT gate is also denoted by a bar, A bar, B bar, something like that, right? So these are the three primary operations. Okay, and the algebra, as I told you, in the digital world, which we only low and high, so that's zeros and ones. And so what we do is that we operate these conjunction, disjunction, negation on these values 0 and 1. So all the inputs, all the variables are either 0 or 1. All right, and how do we operate them? There are some two basic laws which we use frequently. These are called DeMorgan's laws. So A dot B, that is the conjunction. When you negate the conjunction, this is nothing but A bar plus B bar. Okay, so this is a way to convert from a conjunction to a disjunction. Similarly, if you want to convert a disjunction into a conjunction, you can use the second DeMorgan's law. So these are very frequently used, and just to keep it's better to keep them in mind. Right, let's come back to a problem and let's just simplify this fellow over here. All right, so what I'll do is that I'll first, from the first term and this term, this complete term, I can take w plus w bar x common. Okay, I'll do that. W plus w bar x times 1 plus z bar, and this third term will come as it is. And now let's just see what is this term. Right, let me call this y equal to 1 plus z bar. Okay, and let's just try to make the truth table for this. Okay, so I am going to make the truth table for y equal to 1 plus z bar. So as I told you, the inputs here is z and the output here is y, which is 1 plus z bar. What are the possible combinations? 0 and 1. Let's just try to evaluate the value of y. It will be 1 plus 0 bar, which is 1 plus 1. 1 plus 1 is 1, right? And then it will be 1 plus 1 bar, which is 1 plus 0, which is equal to 1. What we see is that whatever will be the input, the output is always high. So what I can say is that y equal to 1. Y is always 1. Let's put this value here. So I'll get w plus w bar x times 1 plus z. If multiplied by some high value, it won't change, so it will reduce to w plus w bar x plus z. Okay, so this is the first. We have simplified it to up to this level. So let's just check if this is one of the options. Okay, so w plus w bar x, no, this is not an option. What we'll do is that we can again further simplify this fellow. How? I'll just tell you. So let me just repeat this over here. W, this have been simplified to w plus w bar x plus z. Okay, so so now what I'll do, I'll use a different law in Boolean algebra. So it goes something like this: f plus gh can be written as f plus g times f plus h. You can easily verify this. It will be f dot f, which is nothing but f, plus fg plus fh plus gh. So this will simplify to this fellow. But I'll compare it with this. Okay, let me write it down over here and let's do term by term comparison. So what I can clearly see is that so from here I can say that f is w, right? Just by comparison, f is w, g is w bar, and h is x, right? And I can write w plus w bar x as f plus g into f plus h. What is f plus g? W plus w bar times f plus h, that is w plus x. So let's put this value over here. So this term a will come out to be w plus w bar times w plus x. This is the first term, and plus z will come as it is. Now let's just focus on this term now. Okay, let me call this term as b. So b equal to w plus w bar, and again I'll draw the truth table for this over here. So what's the input? Input only is w, right? What's the output? Output is w plus w bar. What are the possible combinations of inputs? Nothing. 0 and 1. That's it. There's only one input. What can be the output? 0 plus 0 bar, which is 0 plus 1 equal to 1, or 1 plus 1 bar, which is 1 plus 0 is equal to 1. Again you see whatever will be the output, b is always high, so b is always 1. We see it again, b is always 1. We put this value here, so a will come out to be 1 times w plus x plus z. So I'm continuing this over here. This will turn out to be w plus x 1 times this simplifies, so a is coming out to be w plus x plus z. I cannot simplify this further because all the terms are just a single variable, right? So we have simplified it to a equal to w plus x plus z. So we have simplified it to a equal to w plus x plus z. Okay, and w plus x, which happens to be our option B over here. Okay, so that completes our problem. In this, what we saw was that first, let me go back to this slide to summarize. So first we saw is that this term is repeating. Okay, so I took this term common, and when we solved this term first, 1 plus z bar, and we saw this nothing, this comes out to be but nothing but 1, right? And this is the expression that we came to, w plus w bar x plus z. And then I saw this first two terms, and then we applied this this function, that f plus gh is nothing but f plus g times f plus h. I applied this by comparison, and then we obtained this expression w plus wr, and then we saw using the truth table w plus wr is nothing but b, the value of b comes out to be 1, and that's we solve it over here. So what I'll do is that I'll just, yeah, no, it's fine. So 1 w plus x plus z, this we found out over here, which is our option B. Okay, all right. So that's so in the same spirit, for using the Boolean algebra, so we have one more problem, which happens to be our problem 3. So in this, what we have is that again the problem is worded very similar to the previous problem. Which one of the following functions is equivalent to the Boolean function x equal to this? So what we are required again is to solve this fellow, and let's see which one of these forms it reduces itself to. Okay, so this is the expression that we have, right? So what I'll do, if you recall that we talked about DeMorgan's laws there, right? In 3 variables, so I'll write it. So DeMorgan laws. So DeMorgan's law, P Q R whole bar, I can write it as P bar plus Q bar plus R bar. Previously we saw in 2 variables, 3 variables, the form remains the same. So here you can see the conjunction is been broken into disjunctions, right? So I'll use this and put this back here. Okay, so this will turn out to be then P bar plus Q bar plus R bar times P plus Q plus R whole bar, right? P plus Q, this is not the same. Note that the plus sign is, first we take the negation and then we add them. Okay, now so what I'll do is that, so now I'll write using second DeMorgan's law, which is the second DeMorgan's law, where we change disjunction, that's P plus Q plus whole bar. I can write it as P bar times Q bar times R bar, right? I can reduce it to this form. Okay, so let's put this fellow again back in here. So now this implies x will turn out to be P bar plus Q bar plus R bar times P bar times Q bar times R bar. So essentially this is the term that I have used it over here, and this is the term that I have this term. Okay, so that's what I have done. All right, so now we have the x as in this format. Okay, let me write it again. This was P bar plus Q bar plus R bar multiplied by P bar Q bar R bar, right? So what I'll do is I'll now distribute this multiplication over here. So this will turn out to be P bar times P bar times Q bar times R bar plus P bar Q bar R bar plus P bar Q bar R bar R bar. Note that it's commutative. So what do you mean by commutative? That AB is equal to BA. So if the term is p bar q bar r bar q bar, you can write it as p bar q bar q bar r bar. You can see that I can shift these terms multiplication as per my wish. Okay, that's what I did here. So that's why we get this form. Now this is interesting. Now p bar dot p bar, what it is? So again, in order to evaluate this, so what I'll do, I'll assume some other function that y equal to p bar dot p bar. Let's just try to evaluate what's the truth table. This is p, this is y equal to p bar dot p bar. Let's say possible combination p can be 0 and 1. Let's calculate what is y. It will be 0 bar dot 0 bar, it will be 1 dot 1, this will be 1, and this will be 1 bar dot 1 bar, that is 0 dot 0 is equal to 0. Now what you can see is that so output is nothing but the inversion of the input, right? What this means is that y equal to p bar dot p bar, this is equivalent to just one negation. Okay, so this means this I can reduce it to p bar. The rest of the terms remain the same, plus p bar. Again, q bar dot q bar, I can reduce it to nothing but q bar using the same logic, plus r bar plus p bar q bar. Again, r bar into r bar is nothing but r bar. This is now again p bar q bar r bar is repeating 3 times. So even if you add 3 values like 0 plus 0 plus 0 will be 0, 1 plus 1 plus 1 will be 1. So what I can do, this is equivalent in digital algebra and this electronics is p bar dot q bar dot r bar. Even if it's repeating 3 times, it's essentially the same, because 0 plus 0 plus 0 is nothing but 0 and 1 plus 1 plus 1 is nothing but 1. Due to this, you can drop the 3 term that comes in here. Okay, so we have simplified it to p bar dot q bar dot r bar. Okay, so p bar dot q bar dot r bar, which happens to be option A. See that, p bar dot q bar dot r bar, which is the same option here. So as I told you, if there's nothing mentioned, just assume that there is a dot or the AND gate in between them. So this is how we solve, this is how we simplify this problem that was given to us, right? Again, just very simple expressions. What we did was that in this case we use the DeMorgan's laws. For the first term, we converted this conjunction into a disjunction, right? And then we obtained this. Then for the second term, again we converted into for disjunction into a conjunction, and we obtained this expression. It's the bottom of the screen, and then I simply multiplied this whole term inside, and we saw that due to the commutative property, I can place p bar anywhere I want, because all these terms are in multiplication, and hence p bar dot p bar we saw is nothing but p bar. Similarly, q bar dot q bar is nothing but q bar, r bar dot r bar is nothing but r bar. This whole expression comes out to be this is nothing but 3 times p bar q bar r bar, and we saw that if you add 3 times 0, it's nothing but 0. If you add 3 times 1, it's nothing but 1 in Boolean algebra. Hence we can drop the 3 term, and the final expression comes out to be p bar dot q bar dot r bar, which is the option A that we see over here. All right, just one more thing, we can also write it as all right, I'll not confuse you further, because what I wanted to say is that was this, you see this p bar q bar dot r, p bar dot q bar dot r bar, you know, p q r whole bar, right? So an alternate form can be p plus q plus r whole bar using the DeMorgan's law. Okay, so both these answers are equivalent. Okay, because sometimes if there is more than one option correct, then you have to pay attention to that. These options only have one option correct, so that's why we are safe with this. Just keep that in mind. All right, now moving on to the next question that we have. So till now we have been what we were doing was that we were solving our problems of digital electronics using 2 approaches. First was the truth tables, which is solved with the first problem, and the second and third problem we had solved using Boolean algebra, right, where we saw some laws, like we saw the f plus gs equal to f plus g and f plus h, and some DeMorgan's laws. Those are laws of Boolean algebra. In this case, we will now move to third approach of the digital electronics, where we solve the problems using something called as Karnaugh maps, or also known as K maps. So there are different approaches, and the idea is that there are, whichever approach you feel comfortable with, you take that approach. So that's why we are exposing you to different ways of approaching a problem. So let's solve this problem using Karnaugh maps or K maps. The question says that consider a logical function y a b c d. What this means is that the output is y. It is a function of a, b, c and d. These are the independent variables a, b, c and d, and the output is y. So what we want is that we want y equal to 1 for a, b, c, d equal to these 4 values. So essentially you can create a truth table for this and solve it using that approach also. There's nothing wrong with that. Okay, we'll solve, in fact, in this session itself, we'll solve some problems where we were given the truth table and then we obtain the expression. Okay, but for this problem we'll stick to the K-maps approach. Okay, but for some other inputs like a, b, c, d equal to these 4 inputs, y is don't care. So I told you the outputs are 0 or 1. 0 or 1. There is something also called as don't care, which means we don't care whether the value is 0 or 1. It will be either 0 or 1. It cannot be something in between, but we don't care, and we denote a don't care by x. We denote a don't care by symbol x. This means either 0 or 1. Okay, all right. So for these 4 inputs, for these 4 sets of inputs, y, the value of y is don't care, means it can be 0 or 1, we don't care about it. For all the other inputs, this means 4 inputs here, 4 inputs here, and rest there can be 16 inputs, right? 2 to the power 4, because the inputs are 4, so 2 to the power 4 equal to, there will be total 16 inputs. So for 8 inputs, for 4 inputs, y is 1. For 4 inputs, y is don't care. For other 8 input values, y is 0. We are required to find minimal Boolean expression for y. Let's just forget about this term minimal for a minute. What we'll do, we'll find just a Boolean expression for y using the K-maps approach. Okay, so this is the problem that was given to us. This is the problem that I've repeated here. What we do is that this is nothing but a K-map. So what I've done here is that first I've drawn first we see how many inputs are. There are 4 inputs. Okay, so we divide it in 2 and 2. So the first to go over here and the second to go over here. So AB value 0 0 0 1 1 1 and 1 0. What the key thing to note here is that you can only change only one variable. So AB value 0 0 here. When you go to this column, you're not changing the value of A. The value of A remains 0, but the value of B goes from 0 to 1. Similarly, when you go from second column to third column, the value of B remains 1, but the value of A changes from 0 to 1. That's how we draw the K-map. And finally, the value of A remains same, but the value of B changes from 1 to 0. Similarly, on these rows, so in the first row, the value of CD is 0 0. The second row, you don't change the value of C, you upgrade the value of D from 0 to 1. And then from second to third row, you don't change the value of T, you just change the value of C from 0 to 1. And finally, from row 3 to row 4, you don't change the value of C, you just change the value of T. So you can clearly see the value here will correspond to the input of 0 0 0 0. Okay, let's do that. So let's see, when AB and CD both are 0, that means in this column, what is the value of Y? So let's see, for 0 0 0 0. Okay, so 0 0 0 0, the value of Y is 0. How do I say that? Because question says that, okay, let's do this way. Let's say when Y is 1, let's populate only that first. So when AB, CD is 0 0 0 1, the value of Y is 1. Value of AB is 0 0, that means this column. Value of CD is 0 1, that means this row. So here I'll put 1, because AB is 0 0, CD is 0 1, this means this value. Next, when AB is 0 0 and CD is 1 1, so AB is 0 0 in this column, CD is 1 1 in this, Y is 1 again. Okay, finally again when AB is 1 0, so AB 1 0 is this row, this column, sorry, and CD equal to 0 1, CD equal to 0 1 is this row, again Y is 1. It's given Y equal to 1, and Y equal to 1 finally for 1 0 1 1. So when the value of AB is 0 0, this means this column, CD is 1 1, just see over here, this means this row, I'll write 1 over here. All right, so so this is what we have obtained. Now next we populate the don't care. So 1 0 1 0, so 1 0 1 0, so 1 0 and 1 0. I told you we denote don't care by X. 1 0 1 1, 1 0, sorry, okay, so there must be a misprint because 1 0 1 1 is also here. Fine, 1 is already here, we don't bother about it. Next is 1 1 1 0, so AB is 1 1, AB is 1 1 and CD is 1 0, so this is X. 1 1 1 1 1 1 1 1, this is X again, and we are told that the rest all of them are 0, so I'll put the 0 everywhere else. Okay, So this is now I have populated the K map. So this means that for all the possible combinations of inputs, there is some value of output. This is another, that's why I told you this is another approach alternative to the truth table. All right. Now we are required to find the Boolean expression. We'll minimize it later. Let's just find out the Boolean expression. Okay. How do we do that? Let me choose a different color. So we try to group all the ones. Okay, let's group all the ones. So if I try to group one like this and this, we can only make squares or rectangles. Okay, so just assume that this is extending over here. Okay, like this loops around. If you imagine that you can see that we can form a square using these four values. Okay, now we'll try to find out what do these four values correspond to. Let's just look at the column here. So AB is 1 0 and AB is 0 0. Okay, so what we'll do is that, so we'll take that. A is changing, so we can't take A, but we can take B. We'll take this. Okay, we'll say it B bar, because output is 1. So if this is 0, this B must be negated. All right, now let's look at the rows now. So since C is changing, C we cannot take, but we can take D. We can take this fellow. We can take this fellow, B times D. Why did you not negate D? Because D is already 1. So if you see B bar D, Y equal to B bar D, we'll populate this. Let's just check. So let's just check when B is 0 and D is 1. When B is 0 and D is 1. So B is 0 in this column. B is 0 in this column. Okay. And D is 0 here. So this must be 0. D is 1 here. This must be 1. D is 1 here. This must be 1. And this we don't care. Alright. Similarly, you go here. B is 0 in this column. And D is 1 in these two rows. Hence, these two will turn out to be 1. So what we see is that based on K map, and if we make a group of all the ones, right, what we'll get is the simplified function. So so what we get is the minimal Boolean. Now once we have obtained this, usually sometimes x can be taken as 1. I told you x can be taken as either 1 or 0. So when we want minimal, this means we take x as 0. Okay, what does this term minimal means? We'll take x equal to 0. If you are required to find the maximal one, right, so then we would have taken this one and one more rectangle would have formed here. We also would have been taken in, then our answer would differ. But in this case, we want a minimal, so we'll take simply x equal to 0, and thus our answer would be y equal to b bar into d, b bar into d, which is, yeah, option D over here. All right. So that's how we approach these the same problem with using the Karnaugh maps. Okay, I'll just summarize this again. So what I'll do is that we'll just make first of all a table like this with all. So there are 4 inputs A, B, C, and D. So there must be 16 cells, right? And we populate the inputs like on the top of the table and on the side of the table, such that they only one of the inputs can change when we jump from one column to other. So here you see the B is changing, from here only A is changing, and then again only B is changing, and you see from here to here, from 4 to first column, only A is changing. Similarly you see in the rows, and then depending on what the truth table is or what the output is, we populate the ones and zeros and X. Finally we see all the boxes, we make, if it's possible, we make the rectangles, right, or squares, or if not possible, then we make those squares and rectangles, and then correspondingly we write the expression for y. How we arrived at 1 here? Because B is 0 here, right, in this column B is 0 and 0 here. A is changing, so we can't take A, and B is 0, so that's why we took B bar. In these two rows C is changing, so we drop C, and D is 1, so we take B bar times T, and we also verified that all the other terms are coming out to be 0, but only these 4 terms are coming out to be 1. Hence this Boolean expression is B bar D. Why minimal? Minimal, we want to minimize this expression, we don't want many terms, so that's why we take x equal to 0. For maximal, if we take x equal to 1, then this square we have to include, and corresponding functions also, corresponding values of, right. Hence the answer is D over here. Okay, now let's move on to our next problem, which is a multiplexer. So if there are any doubts still here, you can ask, or any point of time for that matter. All right, no doubts, then let's proceed. So the problem 5 says that for the digital circuit shown in the figure, which of the following expression describes the function y? So you see this is a multiplexer. This is a 2:1 multiplexer. 2 cross 1. That's how it's written, because there are 2 inputs and 1 output. Okay, that's how it's written. 2:1 multiplexer. Okay, and we are required to find what is the expression for this y. So there are many ways of doing it. As I told you, what we'll be discussing is through the format of Boolean algebra. Okay, I told you there are 3 approaches that you can take. First is the Boolean algebra. Second is you can draw truth tables, and the third is K-maps. All right, there are 3 different approaches available to you, so I'll be sticking to the first one over here. All right, so let's just first understand what a multiplexer actually does. So every multiplexer will have n select or control lines. So you see this is called the select line or control line. What it does is that it selects one of these inputs. You imagine multiplexer as a series of many switches. Okay, you can see this is first switch, this is second switch. So at one point of time, that's what the third point says, only one input is routed to output. So only one input, one of these switches will be closed depending on the value of x2, and this is the controller. Hence these are called the controller select lines. Okay, so if there are n select lines, n in this case is 1, right? So if n equal to 1, then what is the maximum number of inputs that you can provide? 2 raised to the power n, which is 2 raised to the power n equal to 2. So you can provide maximum 2 inputs. Okay, and depending on the value of x2, the select line here, either this switch will be closed or this switch will be closed. Okay, and this is denoted using this truth table. Let's say that the value of controller select, this is x2 in this case, is 0. This means the bottom switch will be closed and the value of y will be nothing but the value of I0. On the other hand, if the value of this controller select line is 1, the second row, then the top switch will be closed and the output will be nothing but whatever the value that is coming to I1. And that's how we denote it using this truth table. Okay, so now this is the truth table which I copied from the previous slide. Now what I'll do is that first let's analyze the top row. Okay, when the select signal is 0. Okay, so this is the diagram now. So select signal, what I'll do, I'll say select signal equal to 0, and we saw that what will happen is that in this case this switch will be shorted, which I denote. Now you can see the switch is closed. The value of y is nothing but that's coming at I0. Okay, and I denote it using this. I denote the output as y0 now because this is the first case. So I denote this as y0. Y0 is nothing but whatever the value is coming at I0, this term, multiplied by x2 bar. Why x2 bar? Because x2 is 0 here, right? So essentially you have to see that these are 2 OR conditions. Either this switch will be closed, as we saw, like here, either this switch will be closed or this switch will be closed. So all these rows are nothing but OR conditions. Either first row will be true, second row will be true. So that's what I see. So first row, this is the analysis. This switch is closed in the first case, and we obtain that y0, that's the output for this case, is nothing but I0 times x2 bar. Why x2 bar? Because this is 0, right? This will be true only when we put a bar over here. So x2 bar times I0. Okay, and the value of I0 is nothing but x1, so this will turn out to be x2 bar dot x1. Now let's analyze the second row. In this case, so this is the diagram, and we see that now when x2 is 1, top switch will be closed. You see this is closed, and the value of y will be nothing but x1 bar, sorry, I1 times x2. Now x2 is already 1, so hence we do not need to put a bar over here. So x2 times I1, the value of I1 is nothing but x1 bar. This is the expression that comes out, that it comes out to be. So we have obtained for the first row, this is the expression. For second row, this is the expression. And we know that only at one given point of time, only one of the switches will be closed. So either this is true or this is true. This is an OR gate kind of condition. Hence, for this multiplexer, either this will be closed or this will be closed. So y equal to y0 or y1. Remember, y0 was corresponding to this fellow, y1 was corresponding to this fellow. So or is getting nothing but a plus sign. Y0 we saw in the last slide is x1 times x2 bar, y1 was x1 bar dot x2. This is nothing but the expression for an XOR gate, and which is denoted by this symbol, right? And so we saw that for this for this 2:1 multiplexer, where the inputs and the select lines are oriented in such a fashion, functionalized nothing but an XOR gate. So the answer here would be XOR gate, which happens to be option C over here. All right. So just a brief summary for this problem. So what we had was, so this is the multiplexer that was given to us, and we see that only at any given point of time only one of these switches will be closed, right? So this is essentially an OR condition. This will be closed or this will be closed. So that's what we did. First we analyzed when x2 is 0, and then we analyzed the output will be nothing but that's routed through x1. So it will, y will be equal to x1 only when x2 is 0. Hence this symbol x2 bar dot I naught. This is the expression because I naught is x1. Similarly for the second row, when x2 is 1, the top switch will be closed like this, and the expression comes out to be x2 dot x1 bar. But this is an OR gate, so y equal to y naught plus y1, and we get this expression which is nothing but an XOR gate, which is our option C. Okay, so this is so in this way, using a multiplexer, you can employ a XOR circuit or XOR topology. Okay, all right. So this is again a second problem. Just in the previous case, if you recall, we had one select line, right? This means 2 raised to the power 1 inputs. Here we have two select lines, S1 and S0. This means 2 raised to the power 2 inputs maximum, right? Hence you see these 4 inputs. Okay, now this is a different problem. Now we are required to draw the truth table. Okay, so first what I'll do is that I'll just so this is the problem. First I'll try to obtain the Boolean expression for y, because then my life becomes a bit simpler. Okay, so let's just do that. Okay, now again just remember that there are just nothing but 4 switches over here. Okay, just please keep into mind that. So assume that there are 4 switches like this, and at any given point of time only one of these switches will be closed. Okay, so let's assume that the bottom switch is closed. This switch is closed when S0 and S1 both are 0, sorry, because then only this input will go. That means B bar dot C bar both are 0. So B bar dot C bar times I naught. This input will go through when both of these are 0, just like we did in the last case. The second case, when will the second switch be closed? This is the OR condition which we saw, because only one of these is closed. In the second condition, I1 will go. When will I1 go? When B is 0 and C is 1. No, this is the LSB, least significant bit. This is MSB, most significant bit. Okay, so 0 0 0 1. So B is 0, hence B bar times C is 1, right? So this corresponds to, so I'll write this corresponds to S1 equal to 0 and S2 equal to 0. This corresponds to S1 equal to 0, S2 equal to 1. Third case is what? When S1 equal to 1 and S2 equal to 0, right? This is high but this is low, then this switch will be closed. So it will be 0 times B times C bar. Why 0? 0 is the input that's coming here. Okay, or let's write it I2. Finally, when will I3 come? I3 will come when both the select lines are high. So let's write this, S1 equal to 1, S2 equal to 1. So I3 times B times C. These are the 4 cases, and the plus sign denotes that only one of these will be closed. Let's now simplify this. So this will be B bar times C bar. The value of I naught is 1. I'll put 1 here, plus value of I1 is A B bar C, plus 0 times B times C bar. The value of I2 is 0, plus the value of I3 is A bar B C. Okay, let's simplify this further. This will be B bar C bar plus A B bar C plus A bar B C. All right, so what I'll do is, from the first 2 terms I'll take B bar common. B bar C bar plus AC plus A bar BC. Now we have seen this form F plus GH before, so what I'll do is that, using a different pen, what I'll do is that, we saw that X we are not using. Okay, let's not use X here, it will get confusing. So we have seen that f plus gh can be written as f plus g times f plus h. Okay, now look at this term c bar plus ac. So I'll write c bar plus ac using the same form. So this is f plus g. This will be c bar plus a times c bar plus c. C bar plus c is always 1 because this low plus high. I can 0. We saw that c bar plus c is always 1. This turns out to be c bar plus c. Alright, so now coming back to this, so we see that this term comes out to be c bar plus a. Okay, let me switch the colors again like this. So it will be b bar c bar plus a bar bc. So this will turn out to be b bar c bar plus a b bar plus a bar bc. So this is the Boolean expression for this output for this multiplexer. All right, let me so this is what I have repeated over here, but we got here. Now remember, we are required to find the truth table, right? So how do you find the truth table? You list all the possible combinations of inputs. Note there are 3 inputs, a, b and c for this problem, a, b and c, and also their inversions here. So I'll quickly write. So 0 0 0 nothing but 1 1 1. This will be 1 1 0 1 0 1. I'm inverting all the 3 columns over here. So this will be 1 0 0. This will be 0 1 1 0 1 0 0 0 1 and finally 0 0 0. A bar is nothing but inversion of this column. That's what negation of this column. That's what I have written. So b bar dot c bar. So 1 times 1. This is 1. A dot b bar. A dot b bar. This is 0 times 1. 0 times 1. This is 1. A bar bc. A bar is 1. B is 0. C is 0. This turns out to be 0. And sum of all these 3. So 1 plus 1 plus 0. This turns out to be 1. Right? Let's do this. B bar dot c bar. 1 times 0. This turns out to be 0. 8 times b bar. I'll do this quickly. A times b bar. A is 0. So this will turn out to be 0. A bar bc. A bar bc. This will also turn out to be 0. A bar is 1. But b is 0. And c is 1. So this will turn out to be 0. So 0 plus 0 plus 0. This will turn out to be 0. Alright. B bar c bar. B bar c bar will 0 times 1. This is 0 again. A dot b bar. This is again 0. Dot 0. This is again 0. A bar bc. A bar is this. B is 1. But c is 0. So this will again 0. 1 0 0. Finally b bar dot c bar. B bar dot c bar is 0. A dot b bar. This will again turn out because a is 0. So a dot b bar will be 0. This will be 1 times b times c. Right. So this will turn out to be 1. And the sum will turn out to be 1 because 0 plus 0 plus 1 is 1. Right. B bar c bar. So this is 1 bar 1 times 1. This is 1. So this is 1 times 1 again. This is 1. And a bar bc is 0 dot 0 dot 0. This is 0. 1 plus 1 plus 0 is 1. Right. B bar dot c bar. 1 times 0 is 0. A dot b bar. 1 times 1 is 1. A bar is 0 times b is 0 but c is 1, but this will turn out to be 0. 1 plus 0 plus 1 plus 0. This is 0 again. This is a bit tedious, but we have to do these things. So this might look boring, but you have to do it with your own paper and pen. 0 dot 1 is 0. Yeah. A dot b bar. 1 dot b bar is nothing but 0. It's turn out to be 0. A bar bc. A bar is nothing but 0 times b is 1. C is 0. This is 0. This is again 0. Finally b bar dot c bar. 0 dot 0 is 0. A is 1. B bar is 0. This is 0. A bar is A bar is 0 dot b is 1. C is also 1. This will turn out to be 0. So this is the expression that this is the output that we obtained. 1 0 0 1 1 triple 0. Okay, 1 0 0 1 1 triple 0. So 1 0 0 1 1 triple 0. Let's see which one of the options can we match. 1 0 0 1 but okay, my answer key says this is the option. Let's just see. 1 b bar dot c bar. This is 0 plus a dot. Okay, so there was 0 plus 1 plus 0. So this is 1, not 0. a mistake that I made. Okay, it's fine. So this turns out to be 1. So 1 0 0 1 and 1 1 0 0. That is the output that we have. 1 1 0 0, which matches 1 0 0 1 1 0 0 1 1 1 0 0. Option B. Quickly summarize, this was the multiplexer that was given. What we did was we first obtained the Boolean expression. For this, we just expanded all the terms over here, simplified this, and we got this Boolean expression at the bottom of our screens. And then finally I populated the truth table for this, listed all the possible combinations of the inputs. The inputs are here A, B and C, like this. And then it's just truth table, it's just Boolean algebra, very simple, 0 times 1 0 plus 1, stuff like that. This was the key part actually, where you have to see what are the select signals, and based on that you had to write the output. So this was the key part. So when both are 0, right, B and C both are 0, then this line will be selected. So it will be I0 times B bar into C bar, right? And then when the LSB is high but the MSB is low, so it will be 0 1, right? So 0 1, then this will be selected. That's why you get I1 times S0 bar into S1, and that's why you get A, B bar, C, and so on. The rest is just nothing but simply ones and zeros playing around with them. Just be careful with them, that's all, right? So first we saw one input, then we saw second input mux. Now we are seeing 3 input mux. The logic remains exactly the same, that at one given point of time only one of the inputs will be routed to the output. So that means based on the select signals, only one of these inputs will get routed, and again we are required to find, this time we are given the truth table and we are required to find the value of these inputs. Okay, remember the previous problems we were given the multiplexer, the configuration that is, and we are required to find the truth table or the Boolean expression. This time it's inverted. All right, so let's do that now. So this is the multiplexer and this is the truth table, but just we are on the same page. So what are the select lines? The select lines here are nothing but A, B and C, right, which are reflected in your truth table over here. All right. Secondly, what are the inputs? So you can see the inputs are on the left of the multiplexer, right? These are the inputs which we are required to populate. All right. These are the corresponding values of inputs. So some combination of D, 0 and 1 will come here. Hence I'm denoting D as the input. Just to be clear, it might not be that there can be D or D bar, it can be 0 or 1 here, but it will be some function of D, right? That's what I mean by D being the input. And finally you can clearly see that output, this Y is the output, which is the rightmost column in this truth table. All right, now let's go ahead and start solving this. What do I mean by that is that we'll take the select lines. Okay, the select lines, so A, B and C, they can be zeros, they can be 8 different combinations, right? Because 2 raised to the power 3. So first case is when the select lines S0, S1 and S2. Okay, again I should clarify, this is your MSB, sorry, this is your LSB, not MSB. This is your LSB and S2 is your MSB, most significant bit and least significant bit. Okay, so first case is that when all the 3 are 0, S0, S1 and S2, all the 3 are 0, which happens to be this case. You can see A, B and C both are 0, right? What I'll do is that in this case, now once we've identified the rows corresponding to 0 0 0, I'll focus only on the output side. So you can see that for this Y equal to, so you look at only this part now. Okay, so what I'm seeing is that Y equal to 0 for D equal to 0 or 1. So it doesn't matter what the value of D is, Y is always 0, right? And we know that for this configuration, Y will be routed to I0, right? So the value of Y, or I should say it like this, say it this in a different way, it's easier to comprehend. All right, so we can see that for all D, Y equal to 0, and for this configuration Y is nothing but can get confusing. That's why I'm just trying to frame my sentences. Okay, for this case, y should be nothing but, because this will be shorted here, y should be nothing but equal to I0, right? And we also obtain y equal to 0 for d equal to 0 or 1. So effectively means by comparison I can say I0 equal to 0. Okay, because it doesn't depend on d. So I0 I have obtained to be 0. Alright, now let's look at the second two rows where A is 0, B is 0 and C is 1. You see A is 0, B is 0 and C is 1 in these two rows. Okay, what's the value of y here? The value of, because now there will be a short circuit using this pathway, right? Using this. Let me select that color itself. So this is, yeah, this color. So right, so what's going to happen is that for blue color, this is the pathway. So y will be equal to I1. And let's see what is the value of y here. So y you can see is clearly 1, right? Y equal to 1 for d equal to 0 or 1. So by comparison we can say that I1 is nothing but 1, right? So I1 here I can simply say is nothing but 1. And similarly for the first two rows, right, for comparison we can say I1 was nothing but 0, sorry, I0 was nothing but 0, which was the case over here. So I0 equal to 0 was nothing but this switch. All right, now let's do the third tuple, which is in the sky blue color. All right, so in the sky blue color the circuit will look something like this. This switch is closed now, something like this. Okay, here I know y will be nothing but I2, and if you see y, here, look at these two. When d is 0, y is 1. When d is 1, y is 0. This means y is nothing but d bar. It's inversion of d. So if d is 0, y is 1. If d is 1, y is 0. So y equal to d bar, right? So this implies, compare these two, I2 will be nothing but d bar. Hence we obtain this input as d bar. Okay, for the next case, which we have dark green color, again this will be the pathway, this. So we'll say y equal to I3 in color green. Okay, y equal to I3, and let's consider this fellow. So you can see that what's the value of y from here. You can see that y is nothing but whatever the d is. So if d is 0, y is 0, d is 1, y is 1. So y equal to d. This implies I3 must be equal to d. So this value we obtain as d. Okay, going to the next row in orange. So in orange we can see y is nothing equal to I4. Y is I4, and we now look at these two columns, right? So again you see that y equal to d. When y equal to 1, whatever the value of d, y is stick to 1. Okay, so y is equal to 1 irrespective of d. This implies I4 is nothing but 1, and hence we write 1 here. Moving forward, for okay, I don't have this color over here. All right, let me do it in this. There's no other option. So for this case, y is equal to I5. So this was the fourth case, and this is the fifth case. Okay, now what's going to happen, we have to evaluate this now. Okay, so here y is equal to, when d is 0, y is 1, and when d is 1, y is 0. This means it's an inversion, 0 to 1, 1 to 0. All right, so this implies I5 is nothing but d bar. I5 is nothing but d bar. For the next case, which is in red, y must be equal to I6. By that I mean this switch will be closed now. Okay, y equal to I6, and we have to see this now, this chunk of truth table, and we'll see y is 0 irrespective of the value of d. So y is 0. This implies I6 will be nothing but 0. I write 0 here. Finally, the last two rows that we have, which correspond to the select signal of 1 1 1. So you see it. So why these two rows? Because in these two rows the select signal was 0 0 1. Hence for 0 0 1 this blue was selected. For 0 1 0 0 1 0 the value will be 2. Sky blue is selected. 0 1 1 0 1 1 it's green. This is selected. Finally, when it's all 1 1 1, these last two rows S2 S1 S0 all are 1. These last two we have to see these last two rows, and we have to consider this chunk of truth table. Here y is nothing but I7. Y is nothing but I7. This means the topmost switch y equal to I7, and we see y is 1 irrespective of the value of t. This implies I7 equal to 1. And now you can clearly see that we have populated the right side, the input side of this multiplexer. As I told you earlier also that all the inputs need not be functions of d. You can see there are zeros and ones also, right? So you have to keep in mind that aspect. All right, so we say 1 0 d bar 1, 1 0 d bar 1, so this is not an option. 1 0 d bar 1, 1 0 d bar 1, d bar 1 0, d bar 1 0, so option B is the correct. 1 0 d bar 1, sorry, it's not 1 0 d bar 1, 1 0 d bar 1, 1 0 d bar 1, d bar 1 0, so option C. 1 0 d bar 1, d bar 1 0. Let me check. Yeah, 7th of C is the correct option. So that's how we did it. Just to quickly summarize, this is a 3 input this is a 8:1 multiplexer. So you can see 8 inputs, so there are correspondingly 3 select lines. So this is the truth table given. So when the select lines are 0 0 0, we see that in the first two rows the select lines are 0 0 0, and correspondingly we say that 0 0 0 purple should be the path. This means y must be equal to I0, which we see over here, and we also see that y is 0 for these two rows, right, irrespective of the value of d. Hence I0 should be 0. Similarly, for the second case, when 0 0 1 select line is 0 0 1, that means these two rows, in these two rows blue pathway is selected, dark blue pathway is selected, and y we know in this case should be I1, and we see that the value of y is nothing but 1 irrespective of for d. So from that we get I1 equal to 1. And similarly for different values of select lines, we select two rows, and correspondingly we evaluate the expression between the I2, the input side, and the D or 0 or whatever be the case, and hence we obtain this WebGear kind of thing, which happens to be our option C over here. So my just advice in these problems is that you just have to be patient. These may be time taking, but there's very less scope of going wrong, because the basics are fairly simple. In this case the basic is that only one of the pathway has to be selected, right? That's how we populate this. Okay, right, so now we're done with the multiplexers. Now we'll just see some this will be very light as compared to the multiplexer that we solved. So now we are going to solve a few problems regarding the Boolean algebra. Okay, so the question says, in the digital circuit shown in the figure, which of the following expression correctly describes the function y? So we are given a digital circuit, and we are required to simplify. We are required to find the value of y. All right. So this is the problem that is given to us, and I have just denoted just two nodes, d here and x here. Sorry. So what I'll do is that now. So let's try to find the value of y first. Okay. You can take two approaches. Either you can go from input to output side, or you can go from output to input side. It's advisable that you go from input to output, right? Because if something breaks in between, you will know. Okay, so this means I first tried to find what is d. Okay, so find d. Now d is nothing but, this is the output of an NAND gate between these two inputs. Okay, so we know the output of NAND gate is the two inputs and a bar. The two inputs here are C and C. You see this input is C, this input is also C. So C dot C, we ANDed them, and then this denotes a NOT. So this is the NOT. C dot C we have seen is nothing but C. So this is C bar. So the expression of D evaluated to be C bar. As a next step, we'll find x, this fellow. So how do we find x? X is again the output of a NAND gate. So x is also output of a NAND gate. So NAND gate, you write the two inputs first. What are the two inputs? Two inputs in this case are A and D. you AND them and you negate them. You see, this is, look at only this fellow. All right, only this fellow in the red box. So what's the value? The output X is nothing but this is the NAND gate, A times T whole bar, right? So this yeah, so A times T whole bar. So I can simply write it as A C bar. The value of D is C bar, like this. And if you apply the DeMorgan's law, it can be written as A bar plus C, right? How do I say that? I'll explain to it in proper manner. So this is nothing but A bar plus C bar whole bar. That's what we do to change from conjunction to disjunction. This is the way we do. This is A and double bar. So this is A bar, this is double bar, is nothing but single. Bar of bar is nothing but the same, right? Now finally we find Y. How do we find Y? Now you just use a different color. So you see this purple square. One of the inputs is X, second input is B, right? So Y is also a NAND gate. So Y will be nothing but X times B whole bar and then negate that. So the value of X is A bar plus C, right, times B and whole bar. Okay, you can again apply DeMorgan's law on this. So it will be A bar plus C whole bar plus B bar. This is the first term, this is the second term. All right. Okay, I'm just going back in circles actually, but okay, it's okay. So it's A bar plus C, and then you again apply DeMorgan's law on this. So this will be A times C bar. Essentially you will get to the same value that we have over here. Okay, A times C bar plus B bar. All right, so we get A times C bar plus B bar, A times C bar plus B bar. Okay, option A. All right, so this was a fairly straightforward problem, at least as compared to the multiplexers. So here what we did was that in the problem given to us, we just find out first the value of the internal nodes. In this case it was D and X. So first find out D, which is nothing but the output of a NAND gate in which both the inputs are C. So C dot C whole bar, which is nothing but C bar. Then we find the value of X, which is nothing but the output of the NAND gate in this red rectangle. So it's A times D whole bar. We apply to DeMorgan's law. Finally, for the purple rectangle, Y was nothing but the NAND output of X and B, X dot B whole bar, and we just apply DeMorgan's law to obtain this simplified expression AC bar plus B bar, which happens to be our option A. Right. In the similar flavor, we have one more problem. So in this case, for the digital circuit shown in the figure, each of the following expressions correctly describes the function Y. So the form remains the same essentially, and our approach will also remain the same. So this is the circuit that I have drawn. So here again, what I'll do is that I have just first label all the nodes that we are required. Okay, so let's just quickly write the values of all the nodes which we can. Okay, so D is, this is nothing but a NOT gate. Okay, so first, so as a first step, let me write the first step here. Find D, E and F. Why I'm putting them together is this is nothing but the negation of, so D is nothing but the negation of A, which is A bar. E is nothing but negation of B. You see B is coming here, so E will be nothing but B bar. F will be nothing simply but C bar. This is the negation of C. We have obtained D, E and F. All right, sorry. So now what I'll do is, as a second step, which let's do here. Okay, find G. Let's find G. Okay, and I'll do it with a different color. Find G. So G is this. Okay, this is G. So G, I can write it. You see, this is nothing but a NOR gate, where the inputs are D and B. So G is nothing but the NOR of D and B. So first I'll do OR and then a NOR. So G turns out to be B plus D whole bar. Let's not solve it, let's just proceed further. And for the final thing, what I'll do is in orange I'll do find h. How do we find h? We look at the bottom NOR gate, this fellow. Okay, so h will be equal to the NOR output of E and F, so it will be E plus F whole bar. All right, so I can write it as E bar times F bar. So value of E bar, E is nothing but B bar, so B bar whole bar, plus F is nothing but C bar whole bar. This turns out to be a very good B plus C. All right, so the value of h turns out to be B plus C, G is B plus T whole bar. All right, now we just require to evaluate Z. All right, so here let's do that. So in Z, I'll again choose the red color. So for Z, now let's do the whole thing. Let's see how it, this is step 4. So y is nothing but Z bar. You see this NOT gate, y is nothing but Z bar. Okay, but what is Z? Z is nothing but NOR of G and H. See this G and H, so I'll write Z equal to G plus H whole bar. This implies y equal to G plus H bar and then a whole bar, Z bar. Okay, double bar gets cancelled out, so it will be nothing but G plus H. Now we know the values of G and H, which are B plus T whole bar and B plus C. All right, let me just check once. Yeah, okay, so what I'll do is simply apply DeMorgan's law over here. So this will be B bar times D bar plus B plus C. D bar we know, D bar was nothing but, so D was A bar, so D bar will be A. It will be A B bar plus A plus C. Okay, A B bar, sorry, plus B plus C, not A plus C. So it comes out to be A B bar, this is the expression for y, plus B plus C. Now if you remember that law, that F plus GH equal to F plus G times F plus H, right? Compare it with this B plus AB bar. So I can write it as B plus A, and this will be B plus B bar. B plus B bar we have already evaluated, this turns out to be 1, so this whole thing turns out to be B plus A. So B plus AB bar turns out to be B plus A. Let's put this value here, so it turn out to be B plus A plus C. All right, looks like we have oversimplified it. Let me just check if I did something wrong or not. Problem 9. Okay, let's do, so this will be A bar and G should be B plus T whole bar, B plus T whole bar, that is correct. That should be B plus T whole bar. Yeah, so this should be B bar into D bar. It should be B bar times D is nothing but A bar, so that will be A times B bar. This G is correct. All right, H is E plus F whole bar, that is E bar dot F bar. E, so that will be B. Okay, so that was a mistake here. It's multiplication, not addition. This is the dot sign here, so this is like this. Okay, so and finally we come here, this is G plus H. Let me do this again. So this is G plus H. Yeah, G plus H, the value of G that we have obtained was b bar times a plus h was bc. B bar times a plus bc, there are no famous expressions so that we can reduce it further, so that will remain our answer here. So that is b bar a plus bc, b bar a plus bc, bc plus bc, this is not plus bc, plus bc, yeah, option D. So that is the correct one. Again, a very similar approach in which we just start from the input side and we keep on evaluating the output of each of the logic gates. And so first we do D, E, F, then G, H, and finally Z, and then Y. We just simplified a bit here because this was a NOT gate, right? Now again, it's a similar problem with a similar type of evaluation, that in the sense that for a digital circuit shown in the figure, find the expression correctly describing the function y. So this was the circuit. This I have reproduced the circuit over here. So let's just quickly find out S and R. Find S and R. So S is nothing but, if you see, S is nothing but Q bar. This is Q. Actually, they are not touching. It's just something like this, not touching. So S is nothing but Q bar. Similarly, R is nothing but, this is the line coming from here, that is P bar. All right. Sorry. Next, what I'll do is we'll evaluate the this fellow. Evaluate X. Okay. This is P. So we'll find X. Now to find X, you can see that this is nothing but an AND gate. So AND gate with two inputs, P and S. So this is P times S. The value of S is nothing but Q bar. So this will turn out to be PQ bar. Okay. So that's the first part. For the second part, we'll try to evaluate the value Z. This is Q. So we'll do find Z. What is Z? Z is nothing but the output of this AND gate, and this AND gate has inputs as Q and R. Q times R. Okay. So this turns out to be, Q will remain as it is. The value of R is P bar. And this turns out to be P bar Q. Fine. Now for the last part, which is over here. In the purple rectangle, what I'll do is find Y. What is Y? Y is nothing but NOR of X and Z. I'll write that. Or in that negation, X plus Z whole bar. So X value is PQ bar plus the value of Z is P bar Q whole bar. Let's see if this is an option. Okay, we have to simplify this. Okay, so let's apply DeMorgan's law. Let's so what I'll do is that let's simplify this before. All right, so DeMorgan's law, it will be X bar times Z bar. It's a value of X, PQ bar whole bar. It's a value of Z, P bar Q whole bar. Let me take this to the next slide. So it's PQ bar whole bar dot P bar Q whole bar. Now you again apply DeMorgan's law over in this bracket. So it will be P bar plus Q bar whole bar times P bar whole bar plus Q bar. This will turn out to be P bar. Okay, just a second, did I make a mistake? This will be nothing but Z is P bar Q, Q is PQ bar, correct? Y is V or X and Z, correct? And then we take a negation, so it will be X bar dot Z bar. Value of X is PQ bar whole bar, correct? Z is P bar Q and then it's whole bar, PQ bar whole bar. Yeah, that is correct. So it will be P bar plus Q times P plus Q bar. Is any option matching? No. Let me simplify it further. It will be P bar plus QP plus QQ bar plus P bar Q bar. So these two terms will be 0. While they'll be 0, I'll explain it a bit. So this is P, this is P bar, and let's say the output is something F, which is nothing but P bar. So it can be 0 and 1. This can be 1 and 0. So this will be 0 times 1, which is 0. 1 times 0, which is 0. So P bar will always be 0. Hence this will be 0. Similarly, Q bar will also be 0. Output we get PQ plus P bar Q bar. PQ plus P. So option A. Right. Just a bit of trouble in the last, but it's fine. The approach remains the same. You find out all the intermediate values of the nodes, so for S, R, P and Q, and then X and Z, and finally you just keep on solving the Boolean expression, and we arrive at option A. Okay, so let's move forward quickly. We are a bit short of time. That's fine, should be fine. All right. On this problem, as I told you earlier also, that in digital electronics or in Boolean algebra, what we typically we have three approaches, as I have been talking about. First is your Boolean algebra, which we solved the last 2-3 problems. Second is your truth table. Third is your K-maps. All right, and I have been telling you that you can interchangeably use them. So in the next problem, and maybe a couple of problems later, we'll see that how to change a truth table into a K-map, and that finally a K-map into a Boolean expression. This will be a comprehensive problem. Okay, so this problem states that consider a truth table given in the figure. This is the truth table. Which of the following expression correctly describes the minimal sum of products form for the logical function y? So we'll see what this term means. Okay, so sum of product means that you multiply the inputs, right? Like you see A bar C, and the other input is A bar C bar D bar, and you sum them. Minimal means you have to minimize them by the Boolean algebra. For instance, we saw that P bar is nothing but 0. So if you encounter any term P bar, you must make it 1. And we also saw that if we see A plus A bar, that turns out to be 1. So this means you obtain the expression first, and then you solve it using Boolean algebra to arrive at a minimal form. You simplify it to the furthest extent. Okay, and this sum of product form means this form. So these are products, you see. These are products. First you obtain the products like this, and then you sum them. You see, that's what we'll do. So the way to approach is that this is the truth table that we know. What we'll do is that we'll draw a K-map corresponding to this truth table. So we saw this earlier also. So there are 4 inputs, A, B, C, and D. So AB will denote the columns, CD will denote the rows. As I told you, they can from one column to other, there can be jump of only 1. So you see only B is jumping from 0 to 1. A does not change. Similarly, from second to third column, B remains from 1 to 1, but A jumps from 0 to 1. Similarly, for third to fourth, B changes from 1 to 0, while A does not change. And from fourth to first, you see A changes from 1 to 0, while B does not change. Similarly, you can see for the columns. Okay, now let's just quickly populate the truth table. So for 0, 0, 0, 0, value of y is 1. Correct? For 0, 0, 0, 1, AB is 0, 0. CD is 0, 1. This means this cell. This is 0. 0, 0, 1, 0. 0, 0, 1, 0. Not this. 0, 0, 1, 0. This value is 1. 0, 0, 1, 1. The value is 0. Next, 0, 1, 0, 0. So AB is 0, 1. AB is 0, 1. CD is 0, 0. This is 1. Next is 0, 1, 0, 1. The value is 0. 0, 1. AB is 0, 0. CD is 0, 1. This 0, 1, 1, 0. 0, 1, 1, 0. This one. The value is 1. 0, 1, 1, 1, the value is 1, and rest all the 8 are 0. Let's put rest all the 8 as 0. Right. Remember, we have to find sum of products. Also, abbreviation is SOP. Alright, so how do we do that? We had already talked about that in a way. It's just that you club all the ones. How do you capture all the ones? You see this. I told you, you can just imagine that they're overlapping, right? That this just rounds off to this, all right? And the second column, second group which I'll obtain is this. Okay, so I cannot go here because I must not take zeros, but I have to take all the ones. So first is I made this rectangle which was like overflowing here but connected over here. Second thing, I made this small rectangle. Okay, so first I'll do what I'll do is that I'll make that small rectangle of a different color to avoid confusion. Okay, so let's just first solve the big rectangle. Okay, so what will be the output corresponding to the big rectangle? So you see that let's just first focus on the rows. So here the CD is 0 0 and CD is 1 0. C is changing, so we don't take C, we only take D. So we'll take corresponding to purple, it will be C. We cannot take because it's changing from, you see, only this and this. C is changing, so we cannot take C, but we can take D because D remains constant. D is 0, but the output here is 1, so it has to be D bar, because only when you negate this you will get the output 1 over here. Okay, now we have finished the rows. Now let's look at the columns. So we look at these columns, these two columns. Okay, so we see that B is changing, so we cannot take B, but we can take A, and A is 0 in both. Similarly multiplied by A bar. Why A bar? Because A is 0 and we have to obtain ones over here, hence A bar dot D bar. So now we have obtained the output corresponding to the purple rectangle. Now what I will do is I will take sky blue, and let's take this fellow. Let's obtain corresponding to this. Okay, so we see is that we have to take only, first of all we see that we have to take this and this, and in this D is changing, so we cannot take D, but we have to take C. C is 1 already, so C is 1. Over here we have to take this column. A and B both do not change because naturally it's only one column. So A is 0, so we multiplied by A bar. B is 1, so we can take B as it is, right? C A bar B. This turns out to be A bar B C, and let me simplify this, not simplify, just rewrite this as A bar D bar. Note that this is an OR because one is here as well, one is here in blue purple rectangle also. Okay, so what we write this is as is, just a second, yeah, we write this as that y equal to, you can just assume that they are y0 and y1. Okay, and y will be y0 plus y1. This is an OR case because it's one here or there. So y0 we saw was A bar D bar plus A bar BC. A bar D bar. A bar D bar, it's here. A bar BC, yeah. So option C. So that will be our answer. Again, fairly simple way, in the sense that you just draw K-map for this given truth table. We saw in one earlier problem also, we did the same thing. Alright, and then we obtained the output corresponding to the purple rectangle, which was A bar dot D bar. How did we do that? Because since C is changing, we drop C. D is 0, but we want 1, so hence the negation. Right. Similarly for these two columns, B is changing, so we don't take B, we only take A, but A is 0 and we want 1, hence A bar D bar. Similarly you see in this blue rectangle, so C does not change, so we take C. Here A and B both don't change, so we take A and B both, but it has to be 1, hence we negate A bar, but B is 1, so we take B as it is, and then we simply OR the two cases to obtain option C. Okay, now up until this point of time we were not considered about that how does the waveform look in time domain. So in problem 12 what we'll see that how in time domain how it changes, how the output actually changes, because remember that we actually measure the voltages. So this voltage has some level 0, this voltage has some level maybe 5, 10, 15, whatever it is, right? So we need to see that how with respect to time how do these change, and this is a good illustration of that. Right, the problem says for the circuit an input waveform shown in the figure. So input waveforms, you see waveforms plural, there are two inputs, and this is an what we know call an XOR gate. We'll talk a bit about this, which plot gives the correct output. So we have to find the output Y for the two input XOR gate. So what's an XOR? XOR is exclusive OR, also written as EXOR. So we saw this earlier, so its symbol is A plus and then encircled and then encircled, plus is encircled. This is the Boolean algebra form, A bar B plus AB bar. So if you try to evaluate this, So AB bar plus A bar B, it's 0 1 1 0. This is the truth table for this. All right. Now the key thing to note is that it's an exclusive OR. What does exclusive mean? Exclusive in very blunt English is mean alone or only. Okay, this means the output will be high only when only one or odd number of inputs are high. So this is a 2 input XOR gate. So only when exactly one input is high, the output will be high. So you see both the inputs are low, so the output is low, 0. Here one input is high, A is 0, B is 1, so output is high. Similarly here one input is high, A is high but B is 0, the output is high. But when the both inputs are high, the output is 0. So the key thing to remember here is that when both the inputs are high, when only one of the inputs is high, the output is high. This is the key takeaway from this. This means I need you to just focus on these two. Just focus on the high, the rest will be low. Okay. So we take this knowledge, and this is the circuit that we have, right? And we know that the expression is A bar B plus AB bar, right? And we take this as the first term, okay? A bar B as Y1, all right? Let's plot this first. So this is the input A, but we need A bar, okay? So A bar means we just flip this. 0 becomes 1, 1 becomes 0, like this. This becomes high, again low, and then A is 0, so A bar becomes high, and then we obtain the graph of A bar like this. B is given to us, and finally I'll plot Y1, which is A bar B. A bar B, this means OR of AND of these two. So 1 times 1, this is 1, so it will be high till here. But A bar goes 0, so the whole output will go 0. Because note, Y1 is AND of these two. It will remain 0. It will remain 0 throughout because both the inputs are 0 here. Here A bar goes high in this period, but B is 0. So the output will remain 0 till B remains 0. Now here, at this junction, A bar is high and B also is high, so the output will rise. And output will continue to be high, but then A bar becomes 0 at this vertical line. It will drop and we get something like this. So this is the Y1 that we have obtained, right? Now what we'll do quickly is we plot the Y2, which is AB bar. So this is the input A, this is the input B. Now we'll quickly plot B bar, which will be something like this. Okay. Next we need AB bar. So A times B bar and this times this. So this is 0. So A times B bar is 0, AB bar will remain 0. Now at this junction, that is here, okay, this will rise because A is also high there. Okay, so this will rise and this will remain high until A goes down. So this means up until this point of time. Now if A is 0, this will remain 0. Now both are high during this time period, so Y2 becomes high, and then it becomes low, and then it continues to be low because you see here it's low. Okay, yeah, so it continues to be low, and yeah, something like this. So this is the Y2 that we have obtained. Now this is the Y1 that we obtained earlier. This is Y2. Y is nothing but Y1 plus Y2. So this means OR of these. What do we mean by OR? Even if one of them is high, the sum will be high. Okay, so Y1 is high, so this will remain high, but in this time both are low, right? In this time period, so this will be low, but then this one rises, Y2 rises, so total output will rise. Then again it will fall because both are 0. Both are 0 during this time. Then Y2 is high, so Y will also be high because this is an OR gate, and this will be low, and then again this will rise from here. Okay, so this is the output waveform that we'll obtain for the XOR gate. Okay, so let's see which of the option matches. So it is high to start with, so this option is incorrect. Note, this is high, and we also know that that from 1 it goes low, and then the 3 low periods, actually 3 low periods. So this option is not correct. 3 low period, this option is also not correct. C is the correct option. You can see that this matches low, and then it goes high, and then it goes low again, high low, high low, high low, high low. So C is the correct option. The key thing to here is just that I broke it down during into two, A bar B plus AB bar, and then we plotted, this is Y1, we plotted Y1, then we plotted Y2, and then simply took a OR of them, and that's how we solve this problem. All right, so now coming back, this we solved a similar thing we solved just 2 questions back for question 11. In this case again we are required to find, this is the truth table is given for 4 inputs A, B, C and D. Y is the output. We are required to find sum of products, and that too minimal. We have already talked about this. Minimal means you obtained sum of products first and then you simplify the Boolean expression to the extent possible, right? That we'll do that first, but then the question asks which term does not appear. So first we'll evaluate the expression, the sum of products, then we minimize it, and then we see which of these terms do not appear. The approach remains the same. So this is the truth table that is given to us. Just to be clear, A, B, C and D, these are the 4 inputs. Okay, that's how we draw the K-map. So again you see that for each column, when you traverse from one column to other, only one of the inputs change. 0, 0, it goes to 0, 1. Only B changes. From here to here only A changes, and then from third to fourth only B changes, and then from fourth to first only A changes. Similarly for rows, when you go from first to second row only D changes, second to third row only C changes from 0 to 1, third to fourth row C remains same, D changes from 1 to 0, fourth to first row D remains same but A changes from 1 to 0. Okay, now let's just quickly populate this K-map. So we see that from 0, 0, 0, 0 the Y value is 0, 0, 0, 0, 1 the Y value is 1, 0, 0, 1, 0, which is this is 0, and 0, 0, 1, 1, this is 1. Okay, 0, 0, 1, 0, 1, 0, 0, which is this cell, this is 1 and 1 again, and then we have 0, 1, 1, 1, which is this, which is 1, 0, 1, 1, 0, it is 0, 0, 1, 1, 0, 0, which is this. Now we get 1, 0, 0, 0, 1, 0, 0, 0, which is this, which is 0, 1, 0, 0, 1 is X, 1, 0, 1, 1 is X, 1, 0, 1, 0 is 0, 1, 1, 0, 0, 1, 1, 0, 0, this cell is 0, then X, 1, 1, 1, 1 is X, 1, 1, 1, 0, which is this cell is 1. Okay, so as we did the last time, we'll first evaluate the Boolean expression. Okay, so first you can clearly see, this here in the purple. Okay, so for the purple I can write this, let's say write it as y1. Okay, so y1 would be, you can see that denote this rows here. So C is changing, we drop that, but we take D. Okay, so D is high, so we take, simply write D. Then we check out these two columns. Okay, so B is changing, we don't take B, we only take A, and A is 0, but we want 1 over here, hence we take it to be A bar. So now I have written this rectangle right in the middle, square rather. Okay, now let me take orange color and let me try to write this fellow. Okay, and this would mean these two rows. Okay, so let's write y2. Y2 would be here you can see D is changing, so we don't take D, we'll take C, right? But C is 0 and the output is 1, it has to be C bar then. And we'll take this column, so this column all the terms will come, so it will be B will come as it is because B is 1, but A is 0, but the output is supposed to be 1, hence we negate A, which is A bar. This is the second term. Now there's one more term left, which you can see over here like this in green. So y3 simply be this row. And all right, so there is a thing that I must tell actually before doing this. Okay, remember we had talked about that x can be 1 or 0, right? If you want to obtain minimal form, we must obtain as large a rectangle or square as possible. This means I'll take this. Okay, I cannot make any other square because if I go here, this is 0, here it's 0, below this is 0. So the maximum I can go is here. I can take this, but it will not impact me much. Okay, so this is the maximum that I can take. All right, so that would mean these two rows. In these two rows, we cannot take D. I can take C. C is 1 and the output is 1. So essentially, I'm taking this X as 1. That's the idea. Okay, so it will be C times, and I'll take this column. This column is AB directly. So A times B. So this is what I obtain. So the total Y, okay. So the Y that we obtain is, Y that I have obtained is A bar D plus a bar b c bar plus abc. So abc, this term is here, so this cannot note, will not appear. abc appears, a bar b c bar appears, a bar d appears, bd doesn't appear, so our answer is b. The key thing in this problem that you must note is this: if we did not take this x to be 1, then there will be like 4 terms. It would have been cab into d bar, right? But we wanted to minimal sum of products, right? How do we minimize this? By taking x to be 1. We want to expand, right? And the more once we expand, right, the more sum of products remains minimal. So you can see that when we took the 4 ones, there were only 2 terms, right? When we took a rectangle, there were 3 terms. So the more once you combine, there will be lesser terms. So you'll move towards minimal sum of products. Hence I took this. Okay, so in this way we got our option to be B, because all other 3 terms were appearing. Right, so this is the same problem as before. Actually, the truth table remains the same. So in this case it's asking, so let me just copy that the other thing first, so that we copy that. Okay, is my screen visible? One second. Okay, so now coming back to the problem. Okay, just a second. Yeah, it is there. Okay, so this is the same in the minimizing logical function y in the truth table. How many don't care conditions need to be treated as 0? So in this, this is the truth table that we have drawn. Okay, this is the same problem. So in this problem it asks is that how many don't care condition. I told you x can be 0 or 1. The questions asks that there are 4 x's here. You can see 1, 2, 3 and 4. So out of these 4 x's, how many are you treating as 0? How many are you treating as 1? So that is the problem that we are required to answer. Okay, and this is the truth table. So you see in this truth table I have taken this x to be 1 and I have taken all other x's, which I again denoted in green color. I have taken all other x's to be 0. Okay, so what I mean is that, so total x are 4, right, and x equal to 0 in 3 cases and x equal to 1 in 1 case. Which was that case? It was this case. Here we took x equal to 1. You can see it here, 1 1 1 1, x equal to 1. The rest x was 0 here, 0 here and 0 here, which you can see in these 3 rows, 0 0 0 1 here. So the answer would be 3. So in 3 of these cases I have taken x to be 0 in order to obtain the minimal sum of products form. Okay, now coming back to the last problem for today, we should be fine. Okay, so in the circuit shown in the figure, which option correctly describes the logical function x? So we have solved these kinds of problems, right, where we were given inputs and then we evaluated the intermediate nodes and then we finally evaluated the final expression. But this is a one step further. Here we are required to plot the waveforms. Okay, so in the circuit shown in the figure, which option correctly describes the logical function x? So we are given input waveforms for a, b and c. We are required to find the waveform of x. Okay, so let's do that. So in this case, so this is the circuit. First I'll label these voltages as we before, y and z. Okay, and let's only consider the blue rectangle first. Okay, in this blue rectangle you can clearly see this is an XOR gate, a and b, a XOR b, right? And as we seen before, this is the truth table. So only when one of the inputs are high, the output is high. I told you this is the key that we had to know. So in this case, only when one of these inputs are high, the output is high. All right, so let's evaluate y now. So y equal to a XOR b and now you want to evaluate y. I told you only when one of the inputs are high, the output will be high. Here both the inputs are 0, so the output will be 0. In this period, a is high, b is 0. A is high, b is 0, so the output will be high. It will be like this. Over here, a is 0 and b is 1. A is 0, b is 1, so it will remain to be high. Here, a is 1 and b is 1, the last row. So y will turn out to be 0. Okay, and then both are 0 again, so this will be 0, right? A is 1, b is 0, a is 1, b is 0, it will rise, it will continue to be high. Then a is 0, b is 1, a is 0, b is 1, it will continue to be high. And then over here, a is 1 and b is 1, 1, 1, it will be 0, it will continue to be 0, and then 0, 0, see the first row, this will be 0. So now we have plotted y, which is the voltage over here. Okay, now again, now we'll try to evaluate z, right, where z is the XNOR for b and c. Okay, this is the symbol b and c. You take an XOR and then you negate it. All right, how will the truth table look like? I told you what's a XOR. When only one of the inputs are high, the output is high, right? So XNOR, you just negate that. This means only when one of the inputs is high, the output is low, right? You see 0, 1, the output is 0, 1, 0, the output is 0. If both inputs are low, the output is high. If both inputs are high, the output is high. This is just the negation of the XOR gate. That's it. And so b and c, so these are the two inputs for this z fellow. Now we'll plot z. B and c both are 0, the output should be high. B and c both are 0, the output should be high. B is 1, c is 0. B is 1, c is 0. Output should be 0, like this, right? It will continue to be 0 over here. Here, now b becomes 1, b becomes 0, c becomes 1, b becomes 0, c becomes 1. So output should be 0. Output will continue to be 0. Now the both the inputs are high for these two time periods. So 1 and 1, 1 and 1, both the inputs are high, the output should be high because this is an XNOR gate. This will be high. And then both the inputs are low, the output is high again because it's an XNOR gate. Now we have obtained the waveform for our node Z. Okay, this. Now this is the circuit again, and these are the nodes Y and Z that we had obtained. Okay, excuse me. Now let's look at this again, this fellow, the blue rectangle that you see, YZ. So what is X? X is clearly Y times Z times C. This is C. You see this? This is C. So X is a, so this is a 3 input AND gate. 3 input AND gate. These are the 3 inputs. And we know the output of an AND gate is high only when all the inputs are high. Okay, I repeat. So we can say that X equal to 1 only if Y equal to Z equal to C equal to 1. These are the 3 inputs, Y, Z and C, right? So what I'll do is, so this Y and Z we had obtained in the previous slides. Okay, I have just reproduced them here. So Y, this is Z and this is C. What we are required to find is X, right? And just recall this line. This is the only important piece of information that we need to recall. We can also draw the truth table, but for an AND gate, it's a very simple truth table that only when all the inputs are high, the output is high. All right, so let's just try to find out. Y is 0 here, so it doesn't matter what. Z is 1, C is 0, so 0 times 1 times 0, it will be 0. Again, for this period, 1 times 1 times 0, it will be 0 again, right? And then for this time period, 1 times 0 times 0, again 0, 0 times 0 times 0, 0. In this time period, it's 0 times 0 times 1, again 0. Then it becomes 1 times 0 times 1, again 0, because in this time period Z is 0, right? Now look at this. 1, Y is high, Z is high, C is also high, so the output, so X, the value of X will remain high. Let's see what happens for this. Y becomes 0, so naturally X will also become 0 because it's an output of an AND gate of this, right? So it will remain 0. And Y becomes 0, Z becomes 1, C becomes 0, so it will remain 0. Okay, so this is the output X that we had obtained. All right, let me just For sake of clarity, let's number this. This is first time period, second, third, fourth, 5, 6, 7, 8. Okay, so what we're seeing here is that very clearly is that the output x remains low throughout except for the 7th time period where it's high, otherwise it's low throughout. So that's our answer. Okay, so let's just find out. Is it this 1 2 3 4 5 6 7 8? Yeah, A is the answer. Okay, because we saw here that 7th time period x is high, otherwise it's 0, which happens to be the case here. Here it's high in 6 and 7. It's not the case here. It's high in 7 and 8, I guess. Yeah. Okay, and here it's high in 8. So we saw that higher only in 7th time period, which happens to be our option A. So yeah, that completes the presentation for today, the problem solving. So just to summarize, in today's class we had I'll quickly summarize this problem. So this is the way we had seen before. We just evaluate what the internal voltages are. So for that, I mean, you evaluate what this y is, z is, and then you find out what the expression for x is. That's what our approach is. And in this case, we are required to plot the waveform. So first we plot the waveform for y, then we plot the waveform for z, and then we plot the waveform for x, because x is nothing but a 3-input AND gate of y, z, and c. So that's why we took this approach, and the option was A. That's for this problem. As far as this whole problem solving session is concerned, we saw that for digital electronics, first of all, the very basic things that there are two levels, 0 and 1, low or high. And we also saw there is something called x, which we don't care. So it can be 0 or 1 depending on our choice, because we don't care about it. So if you want it to be 0, we can take it to be 0. If you want it to be 1, we can take it to be 1. It depends on us. Secondly, we saw that to approach these problems, there are 3 different approaches that you can take. First is the Boolean Algebra approach, right, where you solve these expressions using DeMorgan's laws and some other properties or laws. Second thing we saw is that you can solve these approaches using the truth table. You draw the truth table. That is, truth table is nothing but the list of all the possible combinations of inputs, and then you evaluate the output based on that. And third approach which we saw was using Karnaugh Maps or K maps, where we put 1 and 0, we populate the tables and so on. And finally, we saw that we applied all this knowledge so that we can obtain the waveforms, which we are seeing in this problem 15 that's on your screen. So that's all from my side, and we are also out of time. So if you have I'll stick around. If you have any doubts, you may ask for this session or any of the previous sessions. Now for the next 2 sessions, by the way, will also be on digital electronics. So if there are no comments or doubts, I'll close this session, and I'll see you next week. All right. Okay.